My name is Katrina Martin, and I'm an associate chemist and formulator for SC Johnson, working on the Mrs. Meyer's Clean Day brand. I am a member of AOCS in participating in the Young Professionals Common Interest Group and the Surfactants and Detergents Division. The Surfactants and Detergents Division support technical programming at AOCS annual meeting, several awards, and other division activities such as today's webinar for its nearly 300 members. Today's webinar, David Scheuing from Clorox Company will be presenting several major concepts in surfactant science and how these concepts connect to the formulation of household cleaning products used daily by consumers. David is the research director for cleaning division R&D group at Clorox Company. He joined Clorox in 1983 with 10 years of previous experience as an analytical chemist in the coatings industry. During his career at Clorox, he has applied Fourier transformed infrared spectroscopy to studies of micelles and characterization of surfactants and interfacial phenomena. David is also the 2018 Samuel Rosen Memorial Award winner. The Rosen Award is presented annually by the Surfactants and Detergents Division to recognize scientists and technicians whose work has led to significant advancement, cumulative advancement, or application of the principles of surfactant chemistry. Nominations for the 2019 award are currently open, and you can find out more information on this by going to aocs.org. If you have any questions during the webinar, we ask that you please type them in the chat bar on the right side of your screen. We'll have time for question and answers at the end of the presentation. There will be a few spots during the presentation where David will be asking questions, and your answers can also be typed in that chat bar, and I'll read the answers for David. With that, I'd like to say thank you, David, for presenting today and sharing your knowledge with us, and I'll turn it over to you.
Well, thanks a lot, Katrina, for that very kind introduction. Good morning, attendees, or afternoon, or evening, wherever you are. I'm honored and humbled by the award and the opportunity to talk to this audience today. I just consider myself a working chemist, trying to make your everyday life a little better every day. And as was mentioned, Professor Rosen honored his father, who was a working chemist, by establishing this award in the Surfactants and Detergents Division. So for this talk, when I say you, I mean you, the consumer. If I'm talking about a scientist, I'll say surfactant scientist. So let's take a walk through your home and see what kind of surfactant science is there. Where should we start? Well, how about the favorite spot, the kitchen? You know, whether you get Blue Apron or maybe local pizza, or maybe you're a gourmet chef, that kitchen counter where you do your food prep, certainly if you have kids, it's going to need cleaning. And there's the issue besides the pizza grease that we want to deal with, and that's bacteria, gram-positive bugs like Staph aureus, or maybe it's relative MRSA that your teenager might have brought home from practice, and gram-negative bugs like Salmonella or E. coli that you can find on your produce. Well, maybe you use a kitchen sponge for cleaning the grease off your counter there, but unless you're sanitizing that tool, you're doing a pretty good job of spreading germs around that countertop. And there are a variety of references you can refer to. I'll flash the reference slides up at the end of the talk. So now, of course, you're not a germaphobe, right? But as long as you're going to be cleaning the peanut butter and jelly off the counter, you might as well be killing the germs. And one way to do that, that's popular today, is use a pre-moistened wipe. These products are becoming more popular. And so as surfactant chemists, we're going to need to formulate a lotion that's able to wet out that non-woven fabric, as well as wet, spread, and clean a variety of household surfaces that it might encounter. So we're going to use a mixed micellar solution on our wipe, and we're going to have to select an antimicrobial compound. Well, let's use a alkyl dimethyl quat type of compound. There are a variety of disinfecting quats available, the so-called BACs or AdBACs, alkyl dimethyl benzyl ammonium chloride. There's ADIBACs, ethylbenzyl, dimethyl ethyl benzyl ammonium chloride, and there's the DDACs where you have dialkyl dimethyl ammonium chloride. And now that you have the secret decoder ring, you can talk a lot more intelligently about such molecules. Now, obviously, these molecules are surfactants, and so when we use them in our formulations, we're going to have to consider several surfactant science concepts when we use them. So a surfactant chemist might look at a bacteria. All right, I'm trying to wet this bacteria. Okay, a gram-positive bug like Staph aureus has an external layer that's primarily peptidoglycan. It's got some cytoplasmic stuff inside in this cytoplasmic membrane that I'm trying to get my quat to disrupt and kill the bug. And gram-negative bugs like Pseudomonas or E. coli are pretty similar, but they have an extra layer on the outside with a little bit more peptidoglycan. Okay, but in fact, here's how a biologist views a bacteria. Very different picture. Very complex outer surfaces we can see. We have proteins, teichoic acids, polysaccharides that decorate the exterior of the cells. And importantly, that phospholipid membrane that we're trying to attack is not on the surface of the bug. So membrane disruption is our target, but that membrane, right, is not exactly on the outside surface. So we have a variety of germs. SEM photos show us, right? We have a variety of different morphologies of bacteria, different shapes, different sizes that our wipes lotion is what we call them when we formulate them. Our wipes lotion has to deal with quite a variety of these organisms. Or maybe you just think of them all like that. That's how I do. So adsorption isotherms is one of the concepts we can use when we think about this problem we're trying to address. And that is surfactant science helps us with step one, right? The diffusion of our quat to the surface of the cell. We do control that. But the other steps are actually controlled by biology. The transport across that outer membrane into the phospholipid membrane or ultimately to various intracellular targets. Biology controls that. Adsorption isotherms on bacteria, though, have been studied and are known. And it turns out in many cases that those adsorption isotherms tend to be either Langmuirian or high affinity. And we'll see why. The number of bugs, the inoculum that we use in the testing of the efficacy of these products matters. How many bugs are on that surface? It matters a lot because, as we just saw, both the intact bugs and the cells that are dead or debris are sinks for quat. Things like teichoic acids and proteins and lipopolysaccharides are great sinks for our quaternary ammonium compounds. But you know, you can even disinfect with good old SDS, sodium dodecyl sulfate. And so what we have here on the left is the log reduction. That is the logarithm of the number of bacteria that we've killed as a function of time for using SDS at various times. What we see is as we add more cellular debris, more lysed cells to the dispersion that the SDS is in, the log reduction slows down and is decreased. Biologists call this self-quenching. The microbes are actually quenching in continuous time. They're quenching the activity of the biocide. And so what that amounts to is biocide concentrations, as you use them, is not constant. This gives rise to really highly nonlinear kill curves, as we're going to see. And the EPA, who regulates disinfecting products, is not going to give us 30 or 40 minutes to achieve disinfection. We have a maximum time of 10 minutes that we need to do our job in. And they tell us also that we need to have, depending on the organism, 3 to 5 log reduction. So the kill kinetics matter a lot, and dealing with self-quenching matters a lot when we're formulating a disinfecting product. So adsorption isotherms, a major concept in surfactant science, can be measured. So here we have on the y-axis the amount of quat adsorbed onto 2 times 10 to the 9th intact Staph aureus organisms as a function of the equilibrium quat concentration. And we have 2 different quats. We have our ADBAC on the left and our DDAC type on the right. Very different scale, notice on the Y scale. The DDAC adsorbs significantly more onto the Staph aureus organisms, and it seems to have a quite different shaped adsorption isotherm. And we've seen step-like isotherms like this when we talk about adsorption of surfactants onto inanimate materials. And that suggests that at lower concentrations, we may have the high energy sites for adsorption filled up first. And then as the adsorption isotherm jumps up, lateral interactions between the surfactants, the quat in this case, can lead to the formation of things like hemimicelles or even bilayers on the surface of the bacteria. So given that we've seen how heterogeneous the bacterial surface really is, it's not too surprising that we have these multi-step adsorption isotherms that are possible. And the difference in the adsorption is directly related to the difference in the kill rates. So again, we have on the left our ADBAC and on our right our DDAC quats compared. And we have again on the y-axis log reduction, that's the number of bugs killed, versus time. We've got 3 different concentrations of each of the quats, and they were run at 2 different temperatures in this reference. But it's really clear that on the right, the DDAC adsorbs more rapidly, absorbs to a greater extent, and it kills more rapidly compared to the ADBAC on the left. So the adsorption isotherms are directly related to the kill kinetics. These curves also point out one other thing that I want to ask if someone's noticed. After about 3 or 4 or 5 minutes, that we reach a plateau in the log R. What does that mean? Who can catch what that actually is implying? Any comments or answers, Katrina?
Nothing has come in.
Trying to make it interactive, that's all. Okay, we'll move on. So the answer is when we hit a log R plateau versus time, the kill rate of the bugs is 0. There's no more killing going on. The quenching effect has taken over, and you could wait for days. You're not going to reduce the number of Staph aureus organisms anymore. So that's the point of these biological kill curves that surfactant chemists aren't real familiar with. All right, but you know, wipes, lotions, we call them lotions, they can't just be micellar quat solutions, right? Consumers want to clean greasy soils, pizza grease, they want to use them in the bathroom to clean soap scum. And the hand feel, the interaction between the surfactant package and the non-woven matters. The mildness of the surfactant package matters. People like fragrance oils, and the formulations have to deal with not leaving behind a lot of residue, or what we call filming and streaking. So our wipes lotions do tend to be complex formulations and depend on mixed micelles of our quat with other surfactants. So we need to pay attention to mixed micelle type concepts. Well, let's think about the first one, the CMC. If we're going to blend our quat with another surfactant, we have the potential of lowering the CMC. And that could be of a concern because lower the CMC, we have lower quat monomer available. Lower quat monomer available could mean lower or slower adsorption onto the microbes. And that's not a good thing because we are, again, limited in the amount of time we have, and we know how many bugs we need to eliminate. So the blending or the mixed Micell CMC really matters. And there are a couple of basic concepts that relate to mixed CMC. When we're selecting our co-surfactant, the equation on the left reminds us that as we change the tail length, as we add 1 or 2 methylene groups to the length of our co-surfactant, right, the CMC can decrease by a factor of 3 to 10, depending on the actual surfactant we're talking about, but it's a significant effect. So small changes in the tail, of course, make a huge difference in CMC. And then on the right, electrolyte matters. For many of our formulations, we need to buffer them. EPA is concerned about pH, and so we'll be adding electrolyte. And adding electrolyte, as we know, can also decrease CMC. The equation on the right reminds us that the log of the CMC scales as the amount of bound counterion and 2 constants, which is directly related to any additional salt that's present in the solution. So an example there would be cetylpyridinium chloride, which is a quat. Its CMC can be reduced by 2 orders of magnitude by adding enough sodium chloride. CPC, by the way, is a very useful quat. That's in your mouthwash. But speaking of electrolytes, the charge on the bacteria matters as well. And so here we see a couple of different E. coli bugs that express different lipopolysaccharides on their surface, and their charge can vary amongst different strains of E. coli. And worse yet, the zeta potential, a measure of the charge on the bacterium, for one of those bugs changes a lot, around between 10 and 50 millimolar electrolyte concentration. So that's a very large shift in the charge of the bug. And that means, again, the potential for a reduction in the quad adsorption and efficacy just by our changing the nature of the electrolyte package in our wipes lotion. So we have to mind not only the electrolyte level and co-surfactant we're using, but we also have to think about the variation between the various bugs that we're trying to attack. Well, we're going to blend our quat with something else. If we select a co-surfactant like an amine oxide, we need to think about the actual mixed micelle composition as a function of pH, because it's amphoteric. Amine oxides at low pH can exist as totally protonated cationic form, and at high pH they're in their zwitterionic form. And so what we have in the plot is a mole fraction of cationic molecules for both the monomer and the micelle as a function of pH for this particular co-surfactant we might pick. And what we see is the monomer and the micelle compositions do not have to be the same. At rather low pH, the monomers are all cationic. They're cationic rich, much higher amount of cationic monomers. And then at high pH, we have exactly the opposite. Now the micellar reservoir, the fraction of cationic molecules in the micelles is a lot greater than the monomers. And because you want to have nice smelling fragrance type wipes lotions, we should realize that fragrance composition also varies with an amine oxide, for example, micellar solution, because the mixed micelle composition is varying. So here's the solubilization of phenethyl alcohol on the right here as a function of the amount of cationic surfactant in the total micelle. Phenethyl alcohol smells pretty nice, sort of smells flowery to me. It's a typical fragrance type component. And what we see is that the solubilization of the phenethyl alcohol goes through a minimum right around where the micelles are about 50% cationic. And we notice in the other plot that at that point, the micelle size is the largest. In other words, these micelles are rod-like, and the solubilization site of something that is polar, a polar oil like phenethyl alcohol, tends to be between the micelle head groups. Well, when the micelles head groups are crowded together and you have rod-like micelles, that strongly disfavors the solubilization of the phenethyl alcohol. And so we have rod-like micelles that are decreasing the amount of phenethyl alcohol at that particular 0.5 cationic micellar composition. So we change the pH, we actually change the micelle composition and affect our perfume solubility quite a bit. Well, the way to think about this is the opposite as well would apply. If we had a fragrance oil that would solubilize primarily on the interior of the micelles in the hydrophobic region away from the head groups, then it can actually change the net curvature of the micelles and shorten or eliminate the rod-like micelles, pushing them back towards spheres. So this idea of two-site solubilization for a given oil of some polarity, or really more properly, its equivalent alkane carbon number, or EACN, is a very real phenomenon that affects, in the end, the net curvature of the system, and in the end affects how much fragrance I can deliver as I change my mixed micelle composition. Well, not all of you like the same fragrance, so we might have to formulate with a variety or a range of fragrances because various consumers like different sorts of fragrances. But we want to do that, right, at reasonable cost, and we want to have one formulation, hopefully, that can deliver all our fragrances. We can cast this problem in terms of the classic fish diagram type of a plot where we use the hydrophilic lipophilic difference concept as the y-axis and our surfactant concentration on the x-axis. When we have a good match between our surfactant system or our single surfactant, when we have a good match of that with our fragrance oil, the HLD is 0. The HLD equation tells us, okay, that's an optimum point for solubilizing that particular oil with a particular EACN. Well, if we have a range of fragrances that show a very small range in EACN, then the HLD range is going to be relatively small, and we should be able to achieve a single phase system with a single surfactant formulation at some concentration, and concentration of surfactant translates to dollars, of course. So when we have a narrow range of HLD to cover, we don't seem to have a big problem. However, in the real world, that's usually not the case. Fragrance oils especially can display a rather wide range of EACN, which means they can exhibit a pretty wide range in HLD for our single surfactant blend we're trying to use. What happens there? We have to turn up our concentration of our surfactant that we're using. More dollars, increased cost. The worst situation though, right, would be if we pick a surfactant package now that is too overall hydrophobic for the HLD range of the oils we're trying to deliver. Now, this mismatch is so large, I have to crank up my surfactant concentration quite a bit, and we go from some dollars to too many dollars in the development of our lotion. So the lesson here is, when we're trying to formulate our nice clear wipe solutions that smell good and clean well, we need to understand the differences in our fragrances early on in the process. All right, so let's pause a second for teaching purposes and consider what are the couple of concepts we've talked about so far. What type of surfactant concepts have I mentioned so far? And let's see if we can name a few of them. Hopefully some answers are coming into Katrina.
Please make sure you put your answers in the chat bar on the side. HLD.
HLD we mentioned, that's right.
Adsorption.
Adsorption isotherms, yep.
CMC.
Good old CMC and how it's affected, yep.
Protonation.
Yep.
Log kill versus quat kill, or quat type, sorry.
Yep.
Adsorption isotherms and complexity of surface properties of critters.
Critters, I like that. Those critters are variable, yep. So you need to worry about adsorption, yep.
Yep, and then quenching.
Yes. Our biocide concentration is not constant. Great, all right. Well, let's wash up after eating with a visit to the bathroom, right? Unfortunately, what are we going to find in the bathroom? Soap scum. Who really likes cleaning soap scum in the bathroom, right? Well, the humorous Dave Barry knows that ASTM actually does have a standard soap scum that we can use when we're evaluating our various formulations and their performance. I'm not sure what kind of mind can actually consider writing comedy about ASTM, but apparently Dave Barry has that sort of mind. Now, as surfactant scientists, we know that soap scum, calcium stearate, really is an insoluble surfactant that we're dealing with. So it's phases of the soap scum matter for our cleaning it. Calcium stearate is too insoluble to form micelles at any temperature, right? So typically in our formulations, we will add a chelant like EDTA salt in order to generate sodium stearate. Now, sodium stearate forms micelles, but not at room temperature. We can see the critical micellization temperature is 67 C, pretty warm. So typically we formulate our soap scum cleaning products with some other surfactant because we're trying to form mixed micelles with the sodium stearate that we're trying to produce. And so we might use something like an SDS or an amine oxide. We can't arbitrarily turn up the amount of EDTA either because it's a salt. And if we arbitrarily add too much, we can actually increase the CMT of the shorter chain soaps like sodium laurate or the more soluble soaps like the oleate, which is exactly not what we want to do. So we can't just turn up the EDTA. So let's look at the equilibrium solubility of calcium stearate as a function of pH and surfactant type. So we have here on the y-axis the equilibrium solubility of calcium stearate for two different systems, one based on SDS on the left and one based on amine oxide on the right. And we see in the details of the plot that just 0.1 molar EDTA doesn't do much. SDS alone also doesn't solubilize very much calcium stearate. But when we have the SDS and the EDTA combined, now we can begin to actually solubilize that very insoluble calcium stearate. On the right, we have a comparison with the amine oxide. Again, amine oxide alone, not so good. EDTA doesn't do anything, but the blend is significantly better at solubilizing calcium stearate than the SDS. There's a 13 times zoom on that y-axis there. So the amine oxide seems to be doing a really better job of dissolving the calcium stearate, and this is at 25 C. This is at room temperature. Sodium stearate itself, right, is not going to form micelles on its own. Well, we can rationalize what's going on there because we have an effect of the surfactant, and of course we have an effect of the chelant at pH, low pH, say 4. EDTA salts are not very good chelants for the calcium, right? So what we have present is stearic acid and a lot of calcium stearate, and the cationic amine oxide is interacting with that. As we move up to pH 7, now our EDTA salts become better chelants, we generate more stearate, and we have stearic acid present as well, interacting with a cationic and zwitterionic form of the amine oxide. Remember, it can change its total micellar composition, right, as a function of pH. And then at very high pH now, our EDTA is doing its job completely. We have primarily stearate anion present. Stearate's not going to be soluble on its own, though, at room temperature. But now we have our zwitterionic amine oxide present in order to form mixed micelles. There have been other literature references, again, on the equilibrium solubility of calcium stearate, comparing with other surfactants as well. In this particular reference, be careful, the solubility is now on a log scale, so there's a very big difference between the amine oxide on the left and the MES methyl ester sulfonate on the right. And again, what we see is the anionic surfactant, the methyl ester sulfonate, even with the presence of the chelant, is not as good at solubilizing calcium stearate as the amine oxide system by comparison. Well, what we realize as surfactant scientists really is what cleaning the bathroom amounts to is understanding mixed micelle synergism or beta parameters. So for the stearic acid MES system at low pH, we have a non-ionic scum, stearic acid, interacting with an anionic surfactant, MES. And beta parameters for such systems are known and measurable, and they're about minus 3.5. But as we turn the pH up, we are actually decreasing the synergism, because at high pH, we actually have an anionic scum interacting with an anionic surfactant. In that case now, the beta parameter is about 0. There's no special synergistic mixing of anionic species like that. So our synergism decreases and our soap scum cleaning decreases. I didn't show the raw data, but for a system like stearic acid and a non-ionic surfactant like an alcohol ethoxylate, again, at low pH, we have a non-ionic scum and a non-ionic surfactant interacting. Not much in terms of synergism. Beta is about 0. It will increase slightly to a minus 3 or so as we raise the pH up and wind up with an anionic scum, stearate, interacting with our non-ionic. But our great performing amine oxide starts off at low pH with a non-ionic scum and a cationic surfactant. Those beta parameters around minus 2.5. And as we raise the pH, we wind up with a system that has an anionic scum, right? Stearate ion interacting with the zwitterionic surfactant. And in that case, the beta parameters are much more highly negative. They can be as far as minus 7 or even greater. So we see that coming down to cleaning the bathroom amounts to understanding mixed micelle synergism in order to solubilize that very insoluble surfactant calcium stearate. Now, besides the published papers that I pulled some of the data from here, of course, we have Professor Rosen's book, Surfactants and Interfacial Phenomenon, that we can refer to concerning beta parameters and mixed micelles. So let's pause there. Any questions or comments about beta parameters?
If you have any questions or comments, please put them in the chat box on the right-hand side.
Anything coming in? I guess not.
Nope, nothing at this point.
Boy, I must have been really, really clear. Everybody has a great command of beta parameters. I hope so. If you don't have a command of beta parameters and you don't want to admit that, that's okay too. There's some references at the end of the talk, and I just wanted to mention that the great classic paper on this would be Holland and Rubin's paper from '83 in J Phys Chem, where the concept of a beta parameter is derived. There's nothing particularly thermodynamic about a beta parameter. It is expressing basically the non-ideality of mixing of two materials in a micelle. It is the beta parameter, as it becomes more and more non-zero, can be measured directly from, very simply, the mixed CMC of a variety of materials, and then one can calculate what beta parameter is. It's a measure of non-ideal mixing. What it is not is a rigorous thermodynamic property, and worse yet, it may or may not be constant depending on the composition of mixed micelles, and there are some interesting references on that, as well as Professor Rosen's book. All right, let's move on then. I bet you figured by now that we're going to have a stop in the laundry room to see Surfactant Science in action. No surprise there, I would think. Well, laundry temperatures are decreasing both in the US and in Europe. And in the US, the American Cleaning Institute actually has a cold water wash initiative. And their recent consumer survey shows that about 45% of loads are done in cold water today. And 3 in 10 folks are saying that they're actually using cold water a lot more than even 2 years ago. So this seems to be a trend that's accelerating. And of course, the reason for that is you can save as a consumer money by eliminating the cost of heating the water. In terms of greenhouse gas effects in North America, doing the laundry is not a very large thing for a given home, and only about 2% of greenhouse gas equivalents really are due to you doing the laundry. But if you think about, there are 100 million installed washers. And so if one load, as the ACI points out, was changed to cold per week, you do wind up with some pretty impressive numbers here in terms of greenhouse gas equivalents saved. 2.3 million tons, 200,000 cars not driven, 5.5 billion miles, power for over 250,000 homes. So changing the temperature of your laundry not only can save money, it will have a real effect on greenhouse gas emissions. And that's behind this initiative. The AISE in Europe has a similar initiative called the I Prefer 30 campaign, I Prefer 30C. And they're making headway as well, although you can see the average wash temps in Europe are still considerably higher than the US, and they haven't met their 30 degrees C yet. Well, certainly we need to understand that triglycerides, especially if you have kids, or maybe some of you have been eating lunch right now, triglycerides are important stains. They're the glue of many stains that you're going to encounter in doing the laundry. And so for us surfactant scientists, right, understanding the changes in solid glyceride, triglyceride behavior as the laundry temperatures go down is going to be really important. And so if you're not familiar, right, fats or triglycerides like tristyrene are triacyl esters, and they're rather bulky. So in the crystalline solid state, they can pack together on the left in this type of form. The 1-2 acyl chains can be parallel, and then the third acyl chain points in the other direction. They sort of form this chair-like shape, and they stack up then in the crystals to form this type of a crystal structure. Or you can have the 1-3 acyl chains parallel and the 2 acyl chain pointing the other way, and they adopt sort of a tuning fork type of structure, again in the crystalline state. So if we start off with something like tristyrene from a liquid and we quench cool it, like what happen if you're frying something and you have a nice grease splatter, or that hamburger juice gets on your shirt because it's warm, right? If we quench cool tristirine from the melt, it forms the alpha phase, and that alpha phase is thermodynamically not stable. It's going to change and anneal over time to the so-called beta prime and beta phase ultimately. In those phases, the acyl chains are a little closer together and more tightly packed and tilted a bit. And so there are significant changes in the intermolecular interactions in those phases of the triglyceride as it anneals. Our food chemist colleagues know that because this annealing process is what's responsible for the blooming of fats onto the surface of your chocolate bars, which is rather unattractive. And our food chemist colleagues already know that they have to use edible surfactants in order to control that phenomenon in their products. So our challenge is how do the changes in a surfactant affect the crystal structure of a solid triglyceride? Well, vibrational spectroscopies like FTIR and Raman are pretty sensitive to intermolecular interactions in crystals. And so we can use vibrational spectroscopy to actually study the surfactant-fat interaction. One way to do that is to use FTIR with so-called ATR, or attenuated total reflectance optics. So what we do in ATR is we send our IR light through an IRE. It hits an interface and it's totally internally reflected, but it establishes a standing wave right at the interface. And now that radiation can interact with whatever is on the surface of the IRE out into space to some sampling depth d sub p that's about a micron or so. And so we can obtain spectra looking from the surface of the IRE out into solution using ATR. This concept is familiar to all of you. If you've ever looked through a rectangular fish tank through the water, you'll notice the back of the tank sort of looks like a mirror at many angles, but if you reach around and touch it with your fingers, your fingertips are going to appear in the mirror. Same phenomenon, internal reflection. Or maybe you've been lying at the bottom of a pool this summer and look up. At many angles, the surface of the water looks like a mirror. Same phenomenon, internal reflection. Well, today there's handy commercial optical rigs we can buy for this experiment. And this design is particularly handy. It has a horizontal internal reflection element that's at the bottom of a trough. So we can fill our trough with our surfactant solution, and we can have a layer of our solid fat right on the IRE surface and study the fat solution interface via infrared spectroscopy. So we can establish our layer of tristirine in different forms on the surface of our IRE, right? That's step one. We can cast the beta form, which is the thermodynamically stable tristirine form. We can cast that from solution and obtain the spectrum of it. And we can then obtain the more unstable alpha form by melting that layer and then quench cooling it to obtain the alpha form. And we see indeed that the spectra are different. The ester carbonyl differs between the beta and the alpha form. The CH2 deformation band is significantly shifted and different. And there are a series of CH2 so-called wagging band progressions that distinguish the two crystal forms of the tristirine. So we cast our layer, we then go to the literature, make sure we have the form of crystal of solid tristirine we want, and then we're ready to do our detergency experiment. So what we do is we have our layer tristirine, and we're going to add a surfactant solution. In this case, we'll use C12E8 in water at two different concentrations, low and high, 0.3 and 0.3. And we'll add that solution to the trough and then obtain infrared spectra every 20 seconds or so. And as the tristirine is solubilized and removed from the IRE surface, the intensity of its bands is going to decrease, and we can plot that. The way we get the spectrum of the tristirine alone is We have our spectra every 20 seconds. Then we go back and subtract the spectrum of water only times some scalar x and obtain the spectra of tristerin and anything else at the IRE surfactant interface. And again, as solubilization occurs and the tristerin is removed from the surface, the intensity of the bands goes down. And we plot several of them to make sure we get the same trend. And what we see here is that both surfactant concentrations, high and low, initially there's a significant removal of the tristerin, but at some point, at a little bit longer times, that removal slows and eventually stalls. Well, why is that? Well, we can do one more subtraction. We can take the spectrum of the interface at any time, and we can subtract the very first spectrum from the spectra at longer times. First spectrum times some scalar, and if nothing happens at the interface, we should be able to null out the complete spectrum, get a straight line. That's not, however, what we see in the experiment. What we see instead is, over time, bands due to beta tristerin grow and increase in intensity over time. In addition, we see the increase in COC bands due to the non-ionic surfactant absorbing at the interface. So ironically, that strong interaction of the alcohol ethoxylate actually, while it's solubilizing some of the alpha form of the tristerin, actually penetrates into the crystal structure, and you can think of it as a partial loosening or liquefaction of the methylene chains of the alpha phase, and that accelerates the annealing so that the chains can reorient into their thermodynamically favored state, which would be the beta phase, which is much higher melting and ultimately not easy to remove. So ironically, our initial attack of the surfactant generates the hardest to remove form of the tristerin, and the detergency shuts down. There's actually been some simulation work on tristerin bilayers dispersed in water with interacting with good old sodium dodecylbenzene sulfonate as a surfactant, SDBS. And what those simulations show is SDBS can also intercalate into those tristerin bilayers without completely disrupting them, but it will disrupt the crystal structure enough such that the gel transition temperature is lowered. And this seems to be related to the same phenomenon we're seeing in infrared. That is, this partial initial liquefaction step can occur without destroying the entire bilayer. But consumers don't have spectrometers. What they care about is getting greasy stuff off of their clothes, particularly with, as we just mentioned, lower wash temperatures. Well, Professor Sabatini's group is doing much more relevant experiments here using a turgetometer and about 0.1% total surfactant, much closer to the real world. What he did was, for a couple of liquid triglycerides, canola and jojoba oil, they used the HLD approach, measured the EACN of those oils, and then blended an extended surfactant with a twin-tailed surfactant to achieve optimum solubilization capacity for those oils, and then did detergency experiments. So we have detergency on the y-axis and temperature on the x, and determined the detergency as a function of temperature for these two liquid oils for these optimum formulations. We can see that the detergency remains very high for these liquid oils and significantly better than a commercial detergent that they used as a reference. They also took the same approach then for semi-solid fats. Coconut oil and palm kernel oil actually have melting points, which we see here by the vertical line, and they again optimized their system for microemulsion formulation of the liquid coconut and palm kernel oil, but then they did detergency at lower and lower temperatures. And we see that the detergency does decrease below the melting point of those two fats, or if you will, as the solid fat index, the solid line increases, detergency decreases. But their performance of their optimized systems are significantly better than a commercial product where as soon as you cross the melting point of those semi-solid oils, the detergency drops off significantly. This is a very nice paper I recommend because it's also got a great example of a true middle phase formation from semi-solid fats detailed there. So we've walked through your home and we've seen surfactant science in a lot of ways in a lot of different areas of your home. You know, the science is used to make your life easier, healthier, and a little bit cleaner every day. And if you think about changes in germs, emergent pathogens, if you think about changes in the nature of the household surfaces that are being installed that we need to clean, you think about changes in energy use in the laundry room, colder temperatures, there obviously is plenty of research to be done in order to deliver on what consumers want. So, hey, I'd like to thank the AOCS and the division for this opportunity, Clorox for recognizing that it really is an important exercise here for us to do, and of course, you are the consumer. I'll flash up the references for now, and it's time for Q&A, I believe, right, Katrina?
Yes, that it is. So if anyone has any questions that they'd like to ask David, you can put them in the chat box to the right. So we have one question that's come in. Does washing at lower temperatures mean using more non-ionic surfactants?
I think it means using, as the Sabatini group points out, any surfactant system you want, but you need to think about optimizing it for the oil you're interested in. And I would advocate triglycerides because I'm a sloppy eater as well. So one could imagine doing selecting from a variety of non-ionic blends with other things. The key is trying to target the oil solubilization because it seems to help even when the fat is semi-solid. And I talked about maybe why that is.
I had a question. In the beginning, you were talking about antibacterial components. Do you see, and then you were also talking about some of the different interactions. Do you see any of the other components that go into the antibacterial products interfering with the antibacterial, like the quats that you're putting in there?
Yes, that would be my major point of formulating a complex quat-containing system. If you select co-surfactants that, for example, take the CMC down by 2 orders of magnitude, now you have quote unquote enough quat, but you don't have very much quat monomer. And even though there's monomer micelle equilibrium, you may reduce the kinetics, right? The rate of kill by selecting co-surfactants that are inappropriate. And that's not good because the disinfection is highly regulated. You don't have forever to achieve that. So the mixed micelle concepts and quat efficacy, yes, they are related. That's why I talked about them.
What about with fragrances? Do fragrances interfere at all?
So we touched on fragrance solubilization, especially the two-site idea. And you could imagine that a fragrance like phenethyl alcohol being up near the head groups, also interacting with the quat, basically through, though, the net curvature of the system in the end. And that, again, I think could negatively affect the quat adsorption kinetics, the kill rates. That's why I showed kill rates.
A question that's come in, how was the surfactant absorption on the microorganisms measured?
Yes, that's reference, I think I'm staring at right now, reference 4 by Denyer. who described it. I don't have it handy, but it was done just like a surfactant chemist would. That is 2 × 10⁹ staph organisms in dispersion is a fair amount of bugs, and typically they would grow the bugs up, dilute them to the proper inoculum level, spin them down into a small pellet. Then they have their solution of their quad in water, put the bugs in, mix it back up very, very well, let it equilibrate for a while, spin the bugs back out, and then measure the clot that's remaining in the solution. If you do that on the proper scale, even like a classical adsorption, I think that's how they did it. Of course, you have to mind your details about the bug inoculum, but the biologists know how to do that. So they treated it a lot like a silica particle.
Are there any other questions? Are there any cases where liquid crystals are used in detergency?
To boost detergency, I think there are many uses of liquid crystals in laundry detergents for structuring the liquid, right? There's a lot of art by a variety of people that works really well on the bulk liquid. If you think about liquid crystals fundamentally for solubilizing oil, they aren't what you want. Why is that? If you encounter liquid crystals in a phase diagram, they don't have or need any oil. And so they're not really great at solubilizing oil if you want to solubilize oil in a microemulsion. And in fact, some of the details of basic phase behavior shows that liquid crystals actually can interfere with microemulsion formation because the liquid crystals have a net zero curvature, like an optimum surfactant formulation would, but they are the surfactant interacting with itself. So it's not a great place to try and solubilize stuff efficiently. Sure, you can do that, and sure, they're used for that purpose a lot, especially in more concentrated products like laundry detergents before they're diluted, or things like toothpaste. Liquid crystals with fragrance oils are well known. It's just not a great detergency approach.
Well, it looks like that's all the questions we have. I'd like to thank you, David, for presenting this information. It was very informative, and AOCS for the opportunity to do this, and everyone who has listened in and participated, thank you so much.
Thanks a lot. Appreciate it.
Thank you.